Impulse VLSI, where we make things possible. Wipro is hiring for an VLSI engineer level 2 with experience 1 to 3 years. This is the continuation video of the detailed answers to the top interview question as we discussed in the yesterday's video. So let's hear it by an expert.
Let us start the real answers in detail for the questions. The first question is common centered improves matching. How exactly? The common centered matching cancels the linear process gradients like doping, thickness, etc. by placing the devices symmetrically so that the devices experience nearly the same average variation. If I can give the example here, the MOSFET Q1 and Q2, whose multipliers are 4 each. And if I draw the layout of this particular schematic, the layout looks something of this sort, right? So the Q2 is placed first, then Q1, then Q1, then Q2. This is the first row of your layout. The same thing goes in the second row with exactly the opposite MOSFETs placed, meaning the Q1 below Q2, the Q1 MOSFET will be placed, and below Q1, the Q2 will be placed. So this actually faces the same variation. So if there is any variation on Q2, the same variation will get applied to Q1 as well. Hence, the all four MOSFETs Q1 will exactly match the all four MOSFETs Q2. Hence, the common centroid will have the perfect matching in the layout. The next question is, if I already use the common centroid for this guy, for this particular circuit, why do I still need dummy devices at the end? So this is the layout which we have used for the common centroid for the above circuit shown here. But when we actually manufacture, so what happens is that the common centroid handles the gradient effects. Like gradient effects can be like etching and all that process variation. So that dummy devices, whatever you place at the end, will absorb those process and etching variations. For example, let's take this is the only layout that we have placed. And if I get the silicon of this particular layout, actually edges here, it may go something of this sort or something of this variation because of your process or etching problem, or every machine will have some tolerance because of that machine tolerance or the process environments. All that matters during the manufacturing stages. So due to which your final etching becomes somewhat of this sort. Or maybe here the below it perfectly etched well and above it did not etch well. So this can have the variation on this Q1, Q2, or maybe it did not have the etching problem on this right side edge and left side edge. So I ideally wanted the etching to be 100% like the square box. Instead, it will have some problem. To avoid such problem, so what we will do is we'll add additional dummy devices at the end where the etching problem may occur at majority or maybe the process variation. So now these two additional four devices at the both ends will absorb those etching problem, maybe those process variation. Hence, the main transistor which we wanted to perform well will be kept intact. The third question is, what happens if DRC passes and LVS fails? For this particular problem, the DRC is just design rule check. Means that it checks only the physical rules, not the functionality. Whereas LVS means layout versus schematic. It actually checks the connectivity and device mismatch. So circuit will not work if there is a device mismatch or the connectivity problem. So if at all the circuit has to work in the layout, the connections of these transistors has to be proper and they have to be well matched. Then only it will work. Hence, the DRC passes LVS fails means it will not work on real silicon. The fourth question is, the guarding prevents latch up. How? The So when we draw the layout of this particular schematic, So this will have the all the routings of the metals done. So that every routing will have the RC involved, resistor and capacitor of the parasitics, right? So that will have uh, the signal problems. So apart from that, this particular garnering, okay, this particular garnering will help us to inject these minority carriers which are there on the transistor during that last step conditions, and will provide the low resistance path to the supply and ground respectively based on the type of garnering we have used. Let us take an example of this. So in this particular example, we have drawn the garnering for this particular MOSFET here, right? This is the P MOSFET. We have source, drain, and gate. Means this PMOS it is fabricated in the anvil here. The yellow color is the anvil. So if you see this particular P MOSFET, we have put L plus garnering here, meaning that if there is any minority carrier leaked from this N plus from this P MOSFET, that will go and sink to this N plus garnering. So hence it will help us to sink all the minority carriers and not to trigger the SCR for the low resistive path for the high current. That's how the garnering will help us to prevent the latch-up conditions. And the last question here is today that if the two transistors are identical in the schematic, will they behave identical in the layout? The answer is no. Why? Because when we draw the layout of the schematic, let's take an example of this guy only. So we have the four transistors each for Q1 and Q2. If I draw the layout, this is how it looks like. So once we draw the layout, we will connect all this drain, gate, source, everything, right? So once we connect that, the every net will have the parasitic again, as we discussed in the previous problem, that R and C involved for every net, every metal. So whatever we metal we use from for this particular net A, and even if I use exact same metal length with for net B, so there will be some parasitic variation from net B to net A due to that layout effects. So hence the MOSFET Q1 and Q2 will not exactly behave in the layout because of RC involved. I hope you found this answers useful. Thank you so much.
I hope you found this video useful. To know more such interview questions, please subscribe to our channel and please share this video to the needy one. Thank you. See you in the next video.